So the first thing that we want to find is anything that can be found by using just the original function. So of all the stuff that we're looking at here, local extreme values, when it's increasing and decreasing, points of inflection, concavity, and asymptotes, the only one that we can find without taking a derivative is the locations of the horizontal asymptotes. So we should hopefully remember that what we want to do is look at the limit as x approaches infinity of f of x, as well as the limit as x approaches negative infinity of f of x. So for infinity, that's our horizontal asymptote to the right. And if we were to plug in a very large number to each piece of this, we get a very large number times another very large number, which is another very large number. So we would have no horizontal asymptote to the right. Everybody good with that part? And what about the limit as x approaches negative infinity of f of x? That one, the x squared minus 3 becomes just a very large positive number. And then the e to the negative infinity drops to the denominator to become e to the infinity. And this becomes infinity squared effectively over e to the infinity. And which one of those grows more rapidly? The denominator should, which means that this should be approaching what value? If the denominator is growing more rapidly than the numerator, our entire fraction should approach 0. Yeah, e to the negative infinity. Yeah, I mean it is 0, but the problem becomes it becomes 0 times infinity. Nick, so if we drop it to the denominator, though, we can see that it's the denominator increasing more rapidly than the numerator. Does that make sense? Okay. All right. And so this tells us that we do have a horizontal asymptote of y equals 0, but only to the left. Everybody good with that? All right, so now we'll take our derivative to do the increasing and decreasing in the local extrema. So f prime of x should be, and we'll need to use the product rule for this, so it'll be first function times the derivative of the second function plus the derivative of the first function times the second function. And we can factor the e to the x out of both of those. So it becomes e to the x times x squared plus 2x minus 3, or e to the x times x plus 3 times x minus 1. Everybody good with the derivative and simplifying it down? We'll set it equal to 0, and we'll look at when it's undefined. So it's equal to 0 when x is -3 and when x is 1. And we can say that it is never undefined. Okay, so we've got two different critical values, critical value of -3 and a critical value of 1. And to determine if we actually get extrema at those points and whether they max or a min occurs there, or where the function's increasing and decreasing, we'll want to make a sign chart. And we'll put -3 and 1 on. We'll plug in a point between -3 and 1, like 0, for example. And since this is a sign chart for f prime, we'll plug it into our derivative. We plug in 0, e to the 0 is positive, 0 plus 3 is positive, and 0 minus 1 is negative. And if you multiply your two positives and a negative, you get a negative and a function that decreases from -3 to 1. Plug in something more than 1, like 1,000, and all three pieces of your derivative here are positive, and your function increases. And if you plug in a very large negative, like -1,000, e to the -1,000 is still positive. It's a very small positive number, but it is positive. And then both of these are negative, which gives us a positive, and our function increases. Everybody good with that so far? So we'll say that our function increases from negative infinity to negative 3, union 1 to infinity. And we'll say that our function decreases from negative 3 to 1. Everybody good with that? All right, then we want to find out what our local max and our local min are. So we'll have to figure out what f of negative 3 is and what f of 1 is. So f of negative 3, we plug in negative 3 to our original function, which was what? X squared minus 3 times e to the x. So that becomes negative 3 squared minus 3 times e to the negative 3, which would be 6 over e cubed. And that's a local, what, max or min? Which would be a local max based on our sign chart. Okay? And it's a local max at x equals negative 3 if we wanted to specify that. And then to figure out f of 1, we'll just plug 1 in. 1 squared minus 3 times e to the first, or negative 2e, and that value is a local min, and it's at x equals 1. Everybody good with that? Any questions on that? All right, and then lastly, we do concavity and points of inflection. So we'll need a second derivative. So f double prime of x. And if we're taking the derivative of e to the x times x squared plus 2x minus 3, we'll again use the product rule. It'll become e to the x times x squared plus 2x minus 3 plus e to the x times 2x plus 2. And when you factor out the e to the x, you get e to the x times x squared plus 4x minus 1. Everybody good with that second derivative? All right, cool. X squared plus 4x minus 1 doesn't factor using rational numbers. So we can just either complete the square, use the quadratic formula with it. Quadratic formula, so that equals 0. We'll use the quadratic formula to find that. Negative 4 plus or minus the square root of b squared minus 4 times a times c all over 2a. We end up with a 20 inside of our square root. And the square root of 20 can be simplified to 2 root 5. And we end up with negative 2 plus or minus root 5. And then we would also say that this is never undefined. And so our only possible points of inflections are at negative 2 plus root 5 and negative 2 minus root 5. I'll go to the next page. We'll make a sign chart for it there. And what's the value between those? So we can test. Right, 0 is, right? Negative 2 minus root 5 is negative, and negative 2 plus root 5 is more than 2, so that's positive. So we'll plug in a 0 into this, and if we plug in a 0, we end up with a positive number times a negative number. So it's concave down between those two. Plug in something very large like 1,000, and you end up with a positive times a positive, so it's concave up. And plug in something like negative 1,000, it becomes a positive times a positive also, and you get concave up. So our concavity, so we're concave up from negative infinity to negative 2 minus root 5, as well as from negative 2 plus root 5 to positive infinity, and we're concave down in between them, negative 2 minus root 5 to negative 2 plus root 5. looking for the actual value of the point of inflection, we need to plug it back into our original equation. We know we have points of inflection there, so we do f of -2 minus root 5, which should be -2 minus root 5 squared minus 3 times e to the -2 minus root 5. And -2 minus root 5, if you square that, should be 4. Let's see, 4 plus 5, which is 9, and then minus the 3, which is 6, and 6 plus 4 root 5. You guys agree with that? Hopefully I did that arithmetic right. Yeah, I did multiply those out, Adrian. So -2 minus root 5 squared is -2 minus root 5 times -2 minus root 5. -2 times -2 is 4. The negative root 5 times the negative root 5 is plus the 5, and then -2 times negative root 5 is plus 2 root 5. And again, another plus 2 root 5. So we got 9 plus 4 root 5, and then we subtract the 3. I just did it in my head. I didn't write it out. So if we do the -2 plus 4 root 5, we're still going to get the positive 4. We're still going to get the positive 5, which is 9. We're still going to get the minus 3, which is 6. And so that's going to give us 6. And then we're going to have a minus 4 root 5 this time times e to the -2 plus root 5. And so our points of inflection are, I'm not going to write them out, but our points of inflection are -2 minus root 5, comma this, and -2 plus root 5, comma that. Everybody good there? Any questions, any issues on any of that process? Everybody is good with that? So let's take a look real quick at the graph. X squared minus 3 times e to the x. So we can see first off our asymptotes, that to the left there is definitely an asymptote of y equals 0. And to the right there is definitely not an asymptote. It's going up towards infinity. We can see our local max at -3, 0.2999, which must be 6 over e cubed. And we can see our local min at whatever it was, 1, I think that was -2e, I believe. And we should be able to see that we're increasing until we get to -3, decreasing from -3 to 1, and then increasing again afterwards. And our points of inflection are at -2 minus root 5, so somewhere over here. It changes from being concave up, coming away from that asymptote, to concave down to hit this local max and go down. And then -2 plus root 5, which is a little more than 0. Somewhere in between here, it changes from concave down to concave up. So we all see all of those different elements on the graph. Everybody good with that? Nick, yeah, we're going to do some sketching today. So yeah, you want to be able to sketch the graphs also. And if you needed to sketch the graphs, a couple other things you might want to be able to find are your x and y intercepts, right? Our x-intercept just set the original function equal to 0, which would have been plus or minus root 3, which is what these two values are. And if we'd plugged in 0, we would have gotten -3 for our y-intercept. Everybody good there? All right, so a couple of things to remember. First off, the second derivative can sometimes be 0, even if there's not an inflection point there. So always do your sign chart to prove it. And one example is x to the 4th, right? Second derivative of x to the 4th. First derivative is 4x cubed. Second derivative would be 12x squared, right? So at x equals 0, the second derivative is 0, but there's no inflection point at x equals 0. It's actually a local min, so make sure you check the sign chart. And also, a lot of times people forget that if the second derivative is undefined, then you could also have an inflection point there. So make sure you look for the sign change on your second derivative, and at places where it equals 0 or places where it's undefined. Just wanted to remind you guys of that before we go on and do some more fun stuff here. So let's say we've got a particle moving along the x-axis. According to this equation, x of t is 2t cubed minus blah, 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 blah. Let's use the first and second derivatives to describe the motion of the particle along the x-axis. Do you guys think you could do that on your own, or do you guys want to go through it together first? All right, Darius says you guys can try it on your own. So take a couple minutes, see if you can figure out when this particle is moving to the right, moving to the left, when it's accelerating, when it's, all that fun stuff. I'll give you a couple of minutes for that. Ready, go. How's this going? You doing all right with this? Finished? Ready to talk about it? All right, another minute. All right, let's talk about this. So first off, we're given a position function. If we're trying to describe the motion, we're going to need a velocity function and an acceleration function. So start with the velocity function. Take your derivative of your position function. So we got 6t squared minus 28t plus 22. And if we want to try and simplify that down to see when it equals 0, we can factor out a 3 from it. So 3 times 3t squared, I'm sorry, 2 from it. 2 times 3t squared minus 14t plus 11. And then we can factor that into 3t minus 11 and t minus 1. And we'll set that equal to 0 to get t equals 11/3 and t equals 1. Everybody good there? And we'll know that this is never undefined because it's a polynomial. So we'll make a sign chart with 1, not a 1, that's a 1. Plug in something between, we'll say between 0 and 1, just because generally if we're talking about t values, we'll say that t is greater than or equal to 0. So something between 0 and 1, like a half, makes this a negative times a negative times a positive. So that'd be positive, which means our particle should be moving to the right from 0 to 1. Something between 1 and 11/3 would be 2. That'll give us a negative and a positive times a positive, so a negative, which means our particle is moving to the left, and something greater than 11/3, like 1,000, will give us all positives, and our particle will be moving back to the right again. So we would say that it's moving right from t equals 0 to t equals 1 and t equals 11/3. Well, we could just say and t greater than 11/3. And we would say it's moving left from t equals 1 to t equals 11/3. Everybody good with the right and left aspect of it? Okay. Then we want to talk about acceleration also. Hold on one second. Nick, yeah, if you wrote an interval notation, that's fine. I'll send it. So from what I've seen from the old AP test, Nick, on the ones that are talking about motion, that they don't seem to care if you do brackets or parentheses. So use the brackets to be safe probably, but I've seen them give points for either one on motion problems. So. All right, so for our acceleration function, maybe our acceleration function should become the derivative of our 6t squared minus 28t plus 22, which will just be 12t minus 28. And that's never undefined, but it equals 0 when t is 28/12 or 7/3. Everybody good with that? Yep, okay, and so we make our sign chart there with 7/3. Something less than 7/3, like 1, we'll make this negative. So it's decelerating from 0 to 7/3, and greater than 7/3, like 1,000, that's positive, so it's accelerating from 7/3 to infinity. And one other thing we might want to note is about the actual speed of the particle. And so somebody remind me, what is the relationship between velocity, acceleration, and speed? Okay, speed is the absolute value of velocity, but how can we tell if speed is increasing or decreasing? Speed is increasing if what? Yeah, when velocity, oh geez, I know how to type. Thought this would be better. Right. Right. Speed is increasing if velocity and acceleration have the same signs, and speed is decreasing if velocity and acceleration have different signs. Right. So from 0 to 7/3, the sign of our acceleration is negative. Are there any overlaps for a negative acceleration here? Looks like from 1 to 7/3 also. So we could say that from 1 to 7/3, our speed is increasing. And also any overlaps of positive. So this is positive from 7/3 to infinity, and this is positive from 11/3 to infinity. So we could also speed is increasing from 11/3 to infinity. And then we could say that they have different signs from 0 to 1 and from 7/3 to 11/3. Everybody good with that or no? Yeah. All right, so any questions on that? All right, so I'd like you guys to start figuring out increasing, decreasing, concavity, all that stuff for this graph, and then we're going to try and graph it. So take a minute or two and try and figure out all that stuff. All right, how are we doing with this? What have we found so far? Did we find anything for this function before taking the derivative if we needed to graph it, perhaps x and y intercepts? So we could set this equal to 0 and factor out the x cubed and find out that this should have intercepts at x equals 0 and x equals 2. And just spread this out a little bit. And then we don't need to bother to find a y-intercept because we've already found the y-intercept, it's 0. But if we plug in 0, obviously we get 0. So we got an x-intercept at 0 and an x-intercept at 2. Everybody good with that? And then I assume you were finding derivatives. All right, so what was your derivative? F prime should have been 4x cubed minus 6x squared. And we could take out 2x squared from that to get 2x minus 3. Setting it equal to 0, so this would be x equals 0 and x equals 3 halves. And with a sign chart, one second. Sorry about that. So if we plug in something less than 0, like a negative number, we got a positive and we got a negative. So we should have a negative, which means our function should be decreasing. Between 0 and 3 halves, like 1, we should end up with a positive times a negative. So we're still decreasing here. And then greater than 3 halves, like 1,000, this should be positive and positive. So now our function should be increasing. Everybody good with that? Hopefully. And if you plug in 3 halves, what's f of 3 halves? We don't need to find f of 0 because we already know that it's 0. What's f of 3 halves? Should be 81 over 16 minus, and then 2x cubed, what is that? 27 eighths, 27 fourths, which gives you what? Yeah, negative 27 over 16. That sounds good to me. And so we know negative 27 sixteenths is, you know, it's around negative 1 2/3-ish. Not exactly, but, you know, around there. So if this is negative 1, negative 1 2/3, right around there somewhere. Everybody good with that point? That's our local min. Okay, and then we'll do a second derivative. Second derivative should be 12x squared minus 12x. And that'll give us, if we take out the 12x, x minus 1. So a point of inflection potentially at 0 and a point of inflection potentially at 1. Make a sign chart for our second derivative. Something less than 0, a negative number, makes a negative and a negative, so concave up. Something between 0 and 1, like a half, gives us positive and negative, so concave down. And something greater than 1, like 1,000, is going to give us positive and positive, so concave up again. And so we know, let's say as x goes towards infinity, this should be going up towards infinity, and as x goes to negative infinity, it should also be going up towards infinity, which should help us to sketch a little bit. We know that we're decreasing down to here. And then we know that we have a point of inflection here, so this turns. And then at 1, and we need to find, I guess we didn't find f of 1, did we? At f of 1 should be, what, 1 minus 2, so negative 1. So we got a point there. So here we turn back to being concave up, hit that point. Oh man, my graph is really bad. Hard to draw on my laptop here. Something like that. It's not perfect, but that's basically what it should look like. Assume that that went through the actual point 1, negative 1 like I wanted it to. Everybody good with that? So there it is, nicely done on Desmos. Looks just like ours, right? Or at least similar to ours, and ours is messy. But any questions on that? Everybody good with that? All right, let's take a look at this one. Take about 5 minutes, see if you guys can work through this one. Ready to go. How's this going? You guys need another minute, or are you guys ready to do this one? All right, another minute. All right, we good now? Ready? First off, let's see what we can do just by setting it equal to 0. So if we set it equal to 0, this first piece gives us x equals 0, so that's one x-intercept. And it also happens to be our y-intercept. And then the other piece, 3 minus 2 cube roots of x equals 0. That should give us 3 halves is equal to the cube root of x. And so if we cube both sides of that, we should get 27/8 is our other x-intercept. And that's a little less than 3.5, right? So here's 1, 2, 3, and actually let's make each 2 boxes 1 again. So right around there. Then we'll use our first derivative. And personally, if it were me to find the derivative of this rather than using the product rule, I would distribute this through first. I'd say f of x is equal to 3x to the 2/3 minus 2x. And then I would take the derivative of that, and the derivative of that should be 2x to the negative 1/3 minus 2. And if we set that equal to 0, or we look when it's undefined, we should see that this becomes 2 over the cube root of x minus 2. So it's undefined at x equals 0. And if we set it equal to 0, that ought to give us the cube root of x equals 1 or x equals 1. So we're looking at two potential local maxima or minima, one at 0, which we already got plotted, and one at 1. So if we plug 1 into our original function, that becomes 1 times 3 minus 2, or just 1. So we've got a point here at 1, 1. And then lastly, we'll do our, actually, we'll do our sign chart first, sorry. So using our sign chart, we'll put on 0 and 1. A negative number in here is going to turn our first derivative into a negative value, because the 2 divided by the cube root of x is going to be a negative, minus a negative will still be negative. We plug in something like a half into here. The cube root of a half is going to be, let's write this, 2 over the cube root of a half is going to be a positive number. And then when we subtract the 2 from it, we're still going to be positive, because 2 divided by something that's less than 1 is larger than 2. And we subtract the 2, we'll still be positive. And then something greater than 1, like 1,000. This is a number that's smaller than 2. We subtract 2 from it, and it's negative. So we should see it's decreasing, increasing, and decreasing. Everybody good with that so far? All right, and our second derivative, just the derivative of 2x to the negative 1/3 minus 2 should become negative 2/3 x to the negative 4/3. And that's negative 2 over 3x to the 4/3. That'll never equal 0, but it's undefined at x equals 0. And we've already found that there's a local minimum at x equals 0, so we should be able to tell that this is not a point of inflection, because you can't have a local minimum and a point of inflection at the same place. So we'll say no point of inflection. And now we'll just go in and we'll draw this. Now we know that the derivative was undefined at x equals 0, which means that we've either got a discontinuity, which we don't have, or we've got a vertical tangent line, which seems impossible if we have a local min or a max, right? We have a local min here. So the only other options are corners and cusps. Corners aren't going to come from something that's not linear. So we must have a cusp at x equals 0. Oh, sorry, I missed a couple things in the chat. No, cube root of a negative is not undefined, right? You can cube root a negative. Cube root of negative 1 is negative 1, right? Because negative 1 cubed is negative 1. Or the cube root of negative 8 is negative 2. Negative 2 cubed is negative 8. Only even roots of negatives are undefined, so you can't square root or fourth root or 100th root a negative. And then, yeah, x equals 0 is not a point of inflection, because x equals 0 happens to be a local minimum, and you can't have a local minimum and a point of inflection at the same place. So since we've already shown that it's a local min, it can't be a point of inflection. You guys both good with your questions or no? Nick, you good? All right, cool. So now what we're saying is that this function decreases. Oh, we need to do our figure out what the sign of this is. No matter what value we plug in for x, this denominator here is going to be positive, because we're going to raise it to the 4th power, which makes it positive, then cube root it. So it'll still be positive, times 3 will still be positive, but then we do negative 2 divided by that. And we'll see that this function is always concave down. Right? No matter what we plug in, it's going to be concave down. So we should be concave down to this local min, but then we should still be concave down as we come back up, which makes sense, because then that's a cusp, right? We got a cusp here, and then we'll have our local max and drop back down, staying concave down through our x-intercept. And it should follow this same thing. We're decreasing to 0, increasing from 0 to 1, and then decreasing from 1 to infinity. Everybody good with that graph? All right, I know we are essentially, okay, Darius, let me see. Yeah, we know it's a cusp, Darius, for a couple of reasons. One, the derivative was undefined at x equals 0. So the only 4 reasons that a derivative might be undefined or a derivative might not exist would be a corner, which we're not going to have if it's not linear, or has linear pieces. The other next option is a cusp, which is what we do end up having. The next option is a vertical tangent line, which we cannot have because we have a local minimum at that value of x equals 0. And so if we have a local minimum, there's no way for that to be a vertical tangent line also. And then the last option would be a discontinuity, but we know there's not a discontinuity there because if we plug in x equals 0, we get 0. Does that make sense? Okay. Any other questions on this one? All right, so we're essentially out of time, so we will stop there. We'll get into the parametric stuff tomorrow. And here's one more problem that I had up here that we were going to do. So why don't you guys write that one down and just see if you can do that one sometime tonight. I'm not going to check it, but first thing we'll do tomorrow is just go through that one. So make sure you have it done before we start tomorrow. Other than that, you don't have any assignments to do tonight, but we will take a short quiz tomorrow on basically everything else that we've talked about, except for this. We won't talk about it. We won't have any increasing, decreasing concavity stuff on it. It'll just be derivative stuff. Actually, no, we'll have the increasing, decreasing concavity stuff also. Sorry. So everything, regular derivatives and all the increasing, decreasing concavity, points of inflection, maximum, minimum, all that stuff will be on there. And we'll do that tomorrow. Plus, we'll do the graphing stuff with parametrics.